Okay, welcome everyone to this our CAWASA Wednesday webinar. I'm Ignacio Jean, the Executive Director at CAWASA, and today we have a special guest with us, a young professional engineer for the past 6 years with experience in both industrial and municipal drinking water sector, who focuses on membrane and media filtration systems, cooling towers, boilers, and wastewater treatment. 5 of those years being with DELCO. She has been involved in both business development and engineering design of projects across Western Canadian provinces. Her engineering background combined with a client-focused role enables her to apply technical expertise, collaborate effectively, and build strong client relationships that drive overall project success. And today we have with us to present, well, the presentation is on A Tale of 10,000 Straws, overview of hollow fiber nanofiltration. And I hand the floor and would like to welcome Kelsie Hubick, our guest presenter today. Thank you, Kelsie, for joining us, and welcome to the Caribbean, albeit virtually.
Thank you. I wish I was in the Caribbean right now. Yeah, thank you for that great introduction. So I'll just jump right into it, I guess. I'm with DELCO Water. Our company focuses on membrane technologies. The bread and butter of the business has been reverse osmosis, nanofiltration, ultrafiltration, and microfiltration. Really anything to do with membranes, and then slowly getting into wastewater membrane systems as well. Which won't be a topic of this presentation today, but just as an overview there. I am presenting from Canada. The company is based out of Saskatoon, Saskatchewan, so kind of right in the middle of the country. So happy to be here. All right, so for the agenda for today, we'll go through a brief introduction on source waters, different types of source waters, and what their water quality consists of, and an overview of membrane technologies. From my understanding, my colleague Andrew, a couple webinars ago, had given an overview of technologies related to reverse osmosis, spiral wound membranes, and ultrafiltration. So we'll go through a refresher of those ones, and then we'll get into the bread and butter of this presentation, which will be the hollow fiber nanofiltration technology, which, interesting enough, is sort of a hybrid technology of the RO and the UF, which was previously discussed. So that's why we'll run through a refresher. And then we'll finish up with a case study of a Northern Canadian water project installation, and then finish up with some takeaways and question period at the end. All right, so source water and membrane technology overview. So what are some common source waters that we have on Earth? So we've got our surface water sources. These are rivers, lakes, creeks, streams, any water that sits on the surface. And then groundwater is any water underneath the ground, so wells and that sort of thing. And then we also have Goody sources. So these are groundwater wells, but under the direct influence of a surface water source. So they'll actually take on the water quality characteristics similar to a surface water source, but also mixed in with the groundwater characteristics. And then if we're talking about industrial applications, there can be a fourth source, and that would be process water. So a stream recycled from somewhere in the industrial facility. An example could be condensate return from a boiler. But our focus for today will just be on municipal applications, drinking water, and potables applications. All right, some more details on surface water. So they're heavily contaminated by human activities because they sit on the surface. Agriculture activities, mining, factory effluents, human and animal waste are common sources of contamination. They're often high in turbidity, and they don't typically have large amounts of dissolved minerals, but more so suspended solids. They vary seasonally, so seasons such as snowmelt or heavy rainfall can introduce new contaminants. And then manganese concentrations. This is kind of important because manganese can be sort of hard to treat and require some specialty treatments technologies, but concentrations are highest in anaerobic or deep water conditions. And we can see spikes of manganese during spring overturns. So groundwater wells or aquifers and wells, there's 3 different types. I won't go into too much detail on the different types, but there's porous media, fractured aquifer, and unconfined aquifers. The most important thing to note with groundwater wells is just because you would have two, in the instance that you have 2 neighboring wells very close in proximity, doesn't necessarily that those 2 wells are going to be exactly the same and have the exact same water quality and constituents contained in it. It all depends how deep the wells are and which aquifer they're actually tapped into. So Goody wells, so groundwater under the direct influence of surface water. So these are groundwater sources, but take on characteristics of surface water through seepage into the ground. So note that an aquifer is defined as a source which can produce useful quantities of water when tapped by a well, but they come in various different sizes and hectares, and water quality is dependent on the level of the aquifer or the well, the depth of the well, and if there is a surface water source near it. So there's 2 definitions that would define a water source is Goody. So number 1, if there's a significant occurrence of insects or other organisms, algae, or pathogens, including Giardia and Cryptosporidium. So these can cause major health side effects for human consumption and require special treatment for those pathogens. And then number 2 is significant and relatively rapid shifts in water characteristics. So if your turbidity, temperature, conductivity, or pH changes rapidly or significantly depending on seasons or climate conditions, then that well could be deemed a Goody well. So if a well is Goody, we're actually going to choose treatment technologies that are treated for surface water. So I'll get into more details on what I mean by that. So before we make any recommendations or decisions on what treatment technology is suitable for a water source, we always start with a water quality analysis. So that will tell us what exactly is in the water. And then once we know what's in the water, we know what to treat for. So this is just a chart describing what each process or separation process is effective at treating. So on the low end to the right-hand side of the graph, we have our reverse osmosis. And this is treating anything in the water that's in a micron range below 0.001. So essentially anything in the water that's dissolved. And then as we move farther down the graph, the treatment, the micron size increases on what the technology is capable of treating. So nanofiltration, ultrafiltration, would be viruses and anything colloidal or suspended. And then on the very end, we have particle filtration. So this would just be standard media filtration, sand, anthracite, or green sand filtration. Usually can treat things that are visible to the naked eye. So human hair is an example, or fine dust particles. So there's two types of membrane operations, or two types of filtration filtration operations. And this would have been a little bit of a refresher from last time as well. So there's dead end filtration and cross flow. So dead end filtration is when the water runs perpendicular to the surface of the membrane and is forced through using low pressure. There's no continuous waste stream with these, as it's just raw water in equals raw water out. And then foulants build up on the surface of the membrane. So with dead end filtration, we usually see rapid membrane fouling, and a need for frequent backwashing and cleanings to keep the membrane surface clean. Secondly, we have cross-flow filtration. So this is where water runs parallel across the membrane surface. As the water is running parallel, there's an applied high pressure that is pushing the water through the membrane and permeated through as permeate or clean water. So with cross-flow filtration, you have a continuous waste stream and also a continuous clean or permeate stream. So that's the main difference between dead end and cross-flow filtration. Where the different membrane types fit in here, reverse osmosis and nanofiltration will be an example of cross-flow, and your dead end filtration would be your hollow fiber ultrafiltration or microfiltration technologies. So these are three examples of different types of membranes. Again, a little bit of a refresher from the previous webinars that DELCO has put on. But we have hollow fiber modules. So this would be either ultrafiltration or microfiltration. They are primarily used for surface waters or goody waters. And then there is the spiral wound membranes. These would be your reverse osmosis and nanofiltration membranes. Primary treatments, you can have them on groundwater, but they would be used as secondary treatment on a surface or goody water source. So the reason for this is reverse osmosis membranes are really good at removing anything dissolved. But if you have any amount of turbidity or suspended solids, those will need to be removed prior to the RO membranes. Otherwise, you'll run the risk of plugging your membranes very quickly. And then the technology that we're going to discuss in more detail today is the hollow fiber nanofiltration modules, which happens to be sort of a hybrid between the two previously discussed. But they're primarily used for surface water and goody water sources. Some other types of membranes that exist on the market but aren't super common for DELCO water to use, but just as an FYI that there are other types out there. Plate and frame modules used for wastewater industrial process water, tubular modules, again, same source as the prior, and capillary modules can either be for surface water, goody, or wastewater. All right, so just a quick overview or refresher on what ultrafiltration and microfiltration actually is. So what is this technology? So it's a hollow fiber technology, primarily for surface water applications, as mentioned before, and we're targeting turbidity and suspended solids and pathogens. So that's where that log removal credit point comes in. For surface water, we're concerned about pathogens, and log removal credits are a way to measure how effective the membrane has been at removing those pathogens. And it's a log removal credit calculation that the system actually does. Typical recovery is about 90 plus recovery. Our projections will show about 90 to 95 plus, depending on what brand of UF module is being used. But you can see the flow path there in the corner of the little GIF or little video there. But the feed water hits the surface of the membrane on the outside, and then the clean water or the filtrate comes through the tube through the inside. So these modules, they look like, I'm going to explain, they kind of look like spaghetti strands or very small straws, all packed together inside of a pressurized vessel. So DELCO's core technology for UFs are the pressurized system, but there are other UF modules on the market. The submerged system, so there's two different types. Pressurized systems are membranes mounted in housings, or the modules are mounted in housings on a skid, and the feed water is forced through the pores using a pressure pump. The submerged system, however, they're more like cassettes. So they're rectangular in construction, and they're placed inside of a tank or an open basin, and feed water is introduced to the basin and filtrate. Rather than using a pressure pump, it's actually drawn through the membrane using a vacuum pump. For the purpose of this presentation, we'll just be focusing on the pressurized systems. And then a quick overview of reverse osmosis and nanofiltration. So reverse osmosis requires an applied pressure greater than the naturally occurring osmotic pressure to push water through the membrane. So when we're talking about cross-flow filtration, this little graphic here is a perfect example to show how that is working. So your water is running parallel to the membrane surface, as shown with the yellow arrows. A pressure is applied in the blue arrows and permeated through. The minerals or anything dissolved in the water stays on the feed or stays on the other side of the membrane and is rejected as concentrate. And then you have your clean water that comes out of the system as permeate. So these membranes look like a flat sheet wrapped around a permeate tube. They're used for primary treatment on groundwater and can be used in surface water applications as secondary treatment. The key water parameters we're targeting: anything dissolved molecules or ions. And typical recovery on these ones is about 75 to 90% recovery. And that's very dependent on water quality and what's all in your water. So there's two types of spiral wound membranes, reverse osmosis membranes and nanofiltration membranes. The two biggest, or the main difference between the two, is just how much dissolved ions a certain membrane is going to allow passage of. So what I mean by that, so an RO membrane and a nanofiltration membrane, if you set them side by side, you would not be able to tell them a difference. They look exactly the same. The nanofiltration membrane is just going to be a looser RO. So it just rejects less TDS, less dissolved minerals than an RO membrane would. Okay, so now getting into the core of our presentation today. So the hollow fiber nanofiltration of what we've branded the Nano FX. So what exactly is this technology? So it's a hollow fiber technology. So it looks like a UF module. It has the same similar construction as the UF, being the spaghetti strands or straws packed inside of a module. But it operates more like an RO or a nanofiltration membrane. So what I mean by that is this module is actually a cross-flow filtration module or membrane. And it contains a nanofiltration surface property, so that allows it to reject DOC, which you would only see with RO membranes and not with the UF. So our key water parameters for this guy, which are super interesting, is the turbidity, suspended solids. Those two parameters are similar to what a UF rejects or treats. But then because of that nanofiltration surface property, it's also going to reject DOC, which is only common for ROs to reject. DOC stands for dissolved organic carbon, so it's a dissolved constituent, so that's what the RO is going to remove. But this one also removes it. So that's what I mean by the hybrid of the technology. Looks like a UF, but operates like an RO. You can get log removal credits also for these. So there's a way to measure removal of Cryptosporidium and Giardia, and that's super important for surface water. As we said earlier, this is primarily for surface water applications, so that's definitely something that is required. And then typical recovery of these ones, like I said, operates more like an RO, so it has a recovery similar to that of an RO. So between 70 and 90%, depending on water quality. So this membrane, like I said, looks like a UF that are made with PVDF construction, but the NanoFX, these modules in particular, are made of polyether sulfone. And why the PES is chosen for this membrane material is this is what is adding the molecular charge on the separation layer of the membrane to allow that rejection of DOC. And then a little bit of other, it will reject a little bit of hardness and other ions as well, but the main takeaway is rejection of DOC. Oh, before I move on, actually, I'll just mention, so because it's a cross-flow filtration and not dead end, it's actually operating opposite as the ultrafiltration membrane. So instead of having your filtrate come outside of these small little tubes, you're actually pushing the feed water through the tubes and permeate out through the side of the membrane. So opposite in that way. And then the cross-flow filtration, so you're going to have a continuous concentrate stream and a continuous clean water permeate stream as well. So this is just a table kind of summarizing the previous 3 slides that we talked about. So the UF is used for turbidity, TSS, and log credits for treatment. RO or nanofiltration, anything dissolved, so your TDS, hardness, and DOC. And then we can see that crossover with the hollow fiber nanofiltration technology, where it's a hybrid. We're going to be able to treat turbidity, TSS, log credits, and DOC. So knowing this, the hollow fiber nanofiltration technology has a very specific application, and it's intended for water sources, well, surface water sources in particular, but that have high organics, color turbidity, but are generally low in hardness. So it's the perfect alternative when you have a surface water source that would be needing a UF and an RO. With this membrane, you can just supply the hollow fiber nano. So these specific characteristics are very common for Northern Canadian surface water sources. and it allows the technology to be a one-step process instead of a two-step process. And it's operationally simpler and easier to operate with just having the one process step. All right, so we'll move into the case study. So this was a DELCO plant, well, actually a comparison of two DELCO plants of similar size, both installed in Canada, but more specifically in northern Canada. The one site was a UF nanofiltration site, and the second site a hollow fiber nano. So, like I mentioned, the two different sites for this case study were chosen just based on the similar surface water characteristics and being similar in size and design. So with this case study, we'll run through what the modeled water quality projections were projecting. So when we were in our design phase, what those projections were showing, and then the actual operating data from the sites. Then we'll look at a performance evaluation, footprints, and process flow diagrams of the two systems, and run through capital and O&M cost comparison. So similar raw water quality. They were Northern Canadian cold surface water source, having similar treatment capacity. So site A was 9.1 liters per second, and site B being 9.3 liters per second, so very similar. So what I want to highlight here shows why the hollow fiber nano, so this is the hollow fiber nano with site B, shines on low TDS waters, low hardness, but maintains very good rejection of DOC color and turbidity. So site A, UF nano, rejection modeled was 100%. Actual rejection on site operating data, 99.6, so very similar. DOC is actually rejecting a little bit higher than modeled. Color, 97. Hardness, better than modeled, and TDS better than modeled. And then iron and manganese rejecting quite well as well. So just really main takeaway from this slide, I guess, is just to show that the hollow fiber nano still has turbidity rejection. The DOC rejection is quite high, but also is great for waters for low TDS and hardness, because we're only rejecting about 40 to 57% of the hardness in TDS. So when you have low hardness in TDS waters, you want to be able to allow as much of those minerals through as possible to maintain your water stability. So some design considerations here for comparing the two. So because the UF and the RO are two totally different processes, they have more footprint and more ancillary equipment as well. So footprint is reduced with just using the hollow fiber nano. It's just a single step process. So your UFRO has feed pumps, transfer pumps, there's backwash and recirc pumps, compressors, CIP, and a brake tank in between the two, typically. Whereas we can see with the hollow fiber nano, we've really reduced how much of that ancillary equipment is required for the full water plant. So relative footprint relative to the technology. So UFRO, so this is showing that for a smaller size system, 250 meter cube per day, that the UFRO is going to be have a 10.4% more footprint relative to the hollow fiber nano. But we see that number come quite, narrow, that window narrows for systems that become much more larger for treatment capacity. So with the 1350 meter cube per day system, there's only a 3.9% difference relative to the hollow fiber nano. And the reason for that is the hollow fiber nano is designed for a flux rate similar to that of the RO and NF, which is much lower than what a UF would be, and I'll explain that more on the next slide. But because of that, you need quite a bit more modules for the hollow fiber nano to maintain that lower flux rate, and so that window of footprint becomes much smaller when you get into larger sized systems. All right, so this is more of a comparison on the flux and how it's more consistent with the RO versus what a UF is typically designed for. So flux of a UF, typical design 40 LMH, whereas the RO is around that 18 mark. And then so we want to design the hollow fiber nano with a similar flux rate to the RO and NF. And that's because of the cross flow filtration. They operate more like an RO. Recovery here. So the second column, again, the hollow fiber nano for this particular site was 76%. The UF and RO both had a recovery of 90% or plus. But when you look at the overall recovery of the entire system of the UF and RO, the total was 81%. So becomes more similar to the hollow fiber nano. And then the third column is just showing the design flow rates being similar. The UF had to be designed for a higher flow rate because it's feeding the RO. Yeah, skip the slide there. Okay, there we go. Just some considerations between the two technologies is chemical consumption. So UF is going to be more chemical consumer when it comes to maintenance cleans and cleanings. And that's to do with being able to maintain the membrane and get clean for organic fouling and TSS and all of that gets built up on the membrane surface. The RO and NF is going to have a online chemical called antiscalant. So this chemical, every time the RO runs, this chemical has to run. So it's an antiscalant. The antiscalant is necessary to prevent scaling of the RO membrane. And then the hollow fiber nano is similar to the UF in the types of cleanings that it needs. A little bit lower frequency needed, and operator involvement is very rare compared to the UF, but very similar. The UF and hollow fiber nano are similar in that, and the RO is fairly different. Okay, so air integrity testing. So this has to do with the log removal credits for Cryptosporidium and Giardia. So most membrane, and this is only specific for UF and the hollow fiber nano, not specific for the RO at all. So most membrane manufacturers will guarantee a higher than 3 log removal credit, but a multi-barrier approach is almost always required. So DELCO typically only guarantees 3 log with our systems. So virus credits are generally assigned after specific demonstration and challenge testing. And what I mean by challenge testing is the air integrity test. So these two systems come on board with air integrity testing mode of operation. And it's a way to test the integrity of the membrane. So if you have any membranes in your module that are broken, you'll notice when the air is introduced into the module, there'll be little bubbles that bubble up. And if you notice that during operations, it's either time to do a little bit of maintenance. You can take the module out of place and pin the specific spaghetti or straw strand that is leaking. Or if it's very significant, you would have to replace the module. So just a little bit more detail on what 3 log or 4 log means. So 3 log reduction is a 99.9% reduction in inactivation of Cryptosporidium or Giardia. 4 log would be 99.99% reduction in the system. So a little bit more detail on why the RO, why this doesn't apply. So log removal credits, it's not possible to do air integrity testing on RO and NF membranes. There's no way to challenge test the RO membrane while it's in the skid. And so because of that, there's no way to ensure that pathogens or viruses are not passing through the membrane, guaranteeing log removal credits just not possible for that type of membrane. Great, and then quick capital costs and O&M costs, and then we'll finish up with a takeaway and summary here. So again, taking the 2 different sizes of systems, the UFRO is obviously going to be more expensive for a smaller size system, and the O&M costs are higher. But again, we see that window actually flip for higher flow rates, so 1350 meter cube per day. The capital cost actually flips in favor of the UF and RO, and that's due to needing more modules of the hollow fiber nano when your system becomes that much larger. However, we still do realize benefits in O&M costs. So the UFRO still is higher than what the hollow fiber nano will be. All right, and finishing up with some takeaways here. So this was just a summary of the removal targets and which each technology is capable of removing. So the hollow fiber nano, it's intended to replace a UFRO process, but for very specific water qualities. So water qualities that are high in organics, color, turbidity, and low in hardness and mineral content. It's perfect alternative to UFRO applications that have those specific surface water characteristics. And that allows the water treatment plant to become more simpler, combining that 2-step UFRO process into just one single step. And then for this table, so models in engineering are important to estimate the system feasibility and performance. And then looking at the real operating data once it is installed can be compared to verify models and practical experience and judgment. And then finally, just summarizing some of our design considerations. So for footprint, generally, so site A, the UF, RO or nano, there was more process equipment required. Site B, the footprint was much smaller, but became more similar to site A as the treatment capacity increased, again, due to needing the higher modules or more module count. Flux and recovery, so UF flux, you can flux them a lot higher. The RO and NF flux is around 17 to 25 LMH, which is consistent with what we would design the hollow fiber nano module to be. And then recovery is similar, 75 to 90% for the hollow fiber nano. And then again, similar for the RO and NF. Chemical consumption in general is higher for a UF NF site. and quite low for the hollow fiber nano. And we can see that reflected in the O&M costs in the last row. Your RO or nano is going to require an online chemical. So it will have online chemicals, but it will also have CIP cleans. Your UF has CIP cleans and maintenance cleans and backwash cleans. Whereas your hollow fiber nano, there's no online chemical at all. So it's just going to be the maintenance cleans and clean as needed. And main reasons in the difference there. So capital cost, I sort of missed that one there, but I'll go back. So for the 1350 meter cube per day, the capital cost favors the hollow fiber, or sorry, favors the UF and NF, like two-step process. But for smaller size systems, the capital cost favors the hollow fiber nano. All right. And that kind of wraps up our summary there. If anybody has any questions, I'm happy to take those now.
All right, guys, please feel free. The floor is open. I hope you have followed this very comprehensive presentation by our guest presenter. I think this is like the second round of us presenting on ultrafiltration systems. So thank you again, Kelsie, for taking time off to make this presentation. The floor is open. I haven't seen any questions in the chat. Please go ahead if you have any, or yes, Dwayne, please go ahead.
Hi, good evening, everyone. Thank you, Kelsie, for coming on board. I know it's hard trying to concentrate, and Canada is playing at the World Cup currently. One question, is there any design considerations for the material being used? The polyether sulfone. I know there's a big push for like more greener engineering, with the microplastics and everything like that. So and I know it's a newbie question, but is there any other material that can be used for the material for the filtration membranes?
Yeah, that's a great question. I know that topic of more green and toxic free, I guess, materials being used in water treatment is definitely coming to more light, I guess. That's a great question. I don't have an awesome answer for you just because DELCO Water is an integrator. So we don't actually manufacture or build any of these membranes. So major membrane manufacturers, as an example, would be DuPont, Veolia, NX Filtration, and Pentair. So yeah, I don't have a great question on the construction of the actual membrane, other than comment on what they reject and the material they currently use. That's a great question. I can try and we partner with them often. I'll take that down and I can probably get you an answer and follow up with you.
Yeah, sure. Appreciate it. Thanks for that. Thanks for the response. Yeah, because I know, yeah, it's a big thing now. So yeah, and so the idea of, probably I know under materials that had that kind of pressure, it'll be kind of difficult. And science is going a long way. Engineering is going a long way. So if you probably have never had the question posed before, but I know the way things are going, I know those questions will be asked.
For sure. Yeah, I appreciate it. Thank you.
Thank you, Dwayne. Kevin, you have the floor. Good afternoon and welcome.
Hi, greetings from South Florida. Good afternoon. Great presentation. Thank you. I really like seeing the comparison. The last time we had a membrane presentation, I asked this question, it sort of builds off the last question, more about toxins. However, in the treatment process, are you seeing in your travels more and more of these types of facilities due to water quality, new water quality regulations for parameters of concern like PFAS? Are you starting to see that? We're seeing that in Florida. So I just thought I'd ask.
Yeah, no, I appreciate that question. In Canada, it's, I would say, a fairly new discussion, but it is becoming more of a discussion. And I know for the United States, just attending some of the water conferences down there and stuff, it's a huge discussion around the states. So yes, it's definitely something that we've ran into. It's just, I want to say, just came into effect probably within the last 2-3 years that regulators are actually requiring water treatment plants to treat for these constituents. So it is still fairly new for us, but it is coming. I will say, yeah.
Thank you.
Yeah.
I think in the chat we have a question from Karen Martinez. How widespread is the use of this technology in Canada and globally, and some of the factors influencing its adoption?
Yeah, so great question. Thanks, Karen. The DELCO Water specifically has about 10 installations across Canada, and there are other integrators that have a few of their own installations as well. So it's becoming more popular in Canada. Globally, I'm not 100% sure, but these modules are manufactured in Europe by NX Filtration, and then there is another competitor, Pentair, I believe, has their own as well. So globally, they're used. I'm just not sure like how many installations or the specific details on that. I would say some of our challenges in the adoption of this technology is how specific the water quality source has to be for this technology to make sense. So, like I mentioned, it would require a surface water source. That surface water source would have to be high in organics, but low in hardness. So it's common for Canadian northern surface waters, but not all surface water sources. That answers your question.
Well, and serious. Yes, he says thanks.
Right.
While we were at you mentioned about where you can apply or use that technology. So I'm thinking in terms of where we have surface water in some parts of our region, where when we have heavy rainfall, where you have high turbidity, what is the threshold within which you can operate such a system?
Yeah, so turbidity specifically, the threshold for that would be, I think the membrane manufacturers, it's about 150 NTU. And they can handle high spikes of turbidity for short periods of time. It's just as long as the 100 to 150 NTU isn't something that's common and going to be a long-term like water quality issue, I guess. They would just operate at a lower flux rate and kind of derate the system, I guess, for that specific time frame that you do have turbidity spikes. And then for hardness and TDS, it all depends how much you need removed, but typically you're only going to get about 50% removal for those constituents. And then DOC, membrane manufacturers will guarantee 80% removal, but our installations and our experience, we've seen about 90 to 95% of that DOC removal. So those are kind of your limits that you're working with there.
Right. Thank you very much. Okay. I don't see any other questions. Do you have any other questions? I don't see any other hands up. So in that
I do
case,
not either.
yeah, well, we'd like to thank you immensely, Kelsie, for taking your time off. And we hope that the game is going well for Canada in the World Cup. Um, I can't get to watch it myself. So yes, thank you very much. I think it's you did bring out a very comprehensive and excellent
I
presentation
think
for us.
Kelsie did better than the Canadian. There it is. Or injury time, and it's 2-1 Switzerland.
Thanks for the update.
Not good. Yeah, the update. keeping an eye on the score. But great presentation, Kelsie. Very, very comprehensive.
Thank you. Thank you, everybody.
Thank you, Valerie, for your commitment and joining us in the wee hours of the morning. I'm Ignatius Jean, signing off, Executive Director at CAWASA, the Caribbean Water and Sewage Association. And this is webinar number 15. Today we had a fabulous presentation on the tale of 10,000 straws, an overview of hollow fiber nanofiltration systems presented by Kelsie Hubick. Thank you very much, everyone. Have a good evening. Bye.
Take care. Bye-bye.